Hello, welcome to Everything Distributed. Today we are going to talk about hash function, and in particular, we want to know what a hash function is and why do we care about it. So let's start with a very simple problem in computer science. I give you an array of size n, and then I want you to find whether an element is inside an array or not. And it has lots of application because it could be that we don't want to have a repetitive elements inside an array, or like based on the element, the value of the element, we need to make different decision. And if we don't know anything about an array, the most straightforward solution is a brute force approach, which I'll check every element inside an array and then to see that whether I find it or not. And for this, what will be the time complexity? Remember, the size of an array is n, so it's all n. And one very simple trick to know is that if an array is sorted, then we can improve the time complexity, the runtime a lot, which we can use binary search, and it's log n complexity. And in practice, can we do any better? Suppose that we don't have an array, we have a set of elements. What can we do? And one key idea that is very useful is the hash function or hash. Hash is a data structure such that you can update an element or retrieve an element from a set in constant time, which is all one complexity. Of course, there's no free lunch, so it's under some conditions. And then the analysis, actually, it's a bit difficult because it's based on some amortized analysis, that there's some math and randomization involved, and it's beyond the scope. But in real world, many of the popular hash function is more than enough for your daily scenarios. Then what do we usually call hash map, or sometimes we hear a hash function? Because in mathematical terms, what is a map? Basically, just I have two sets of values. You can consider it as an input or output. It tells you the relation. And if you are into math, here's the summary and abstract from Wikipedia. Feel free to check it. Then in terms of what we computer science need to know, what's a map? It's a relationship, and then you have a pairs, which is a key and a value. So how do we use it? Is that for a given key, we want to find out the value, use some predetermined function, and then that's what we call hash function, that tells you the relationship or the links between some values and some keys. So kind of formally, what we do is that we have a hash function h, and then the relationship between value and key, just that you input a value, the value is treated as the input to your hash function, then the key is the output of the hash function. Okay. Then the idea of a hash table basically is built around this predetermined hash function, and you can think of it as a generalized idea of an array or a set, such that key may not be just an integer. So key could be a string or actually any kind of object, as long as your hash function can map to it. And the key idea is this hash function, and what it does is that you have HA or H value, and then it will output the key. So it tells you, roughly speaking, is the index of the object. And then that index can be searched or let's store in some kind of data structure very efficiently, so that it's a mapping between value and key, and such that you can do update and retrieval in all one time, so in a constant time. And then the whole process can be done very efficiently. And one key idea is that this relationship has to be deterministic. Otherwise, you don't know how to find your data. Okay, and that's the big idea about hash table. And then here are some exercise for you. Suppose that we have set of strings, like your values are all these only three elements. It's ABD, DF, GHI. Then I want to create a hash table. You can think of an array, and such that the array or table has a size 5. You want to map the value to the element or to the final index for your table. Then what you need to do is that to define your hash function. And then actually that if you don't care about efficiency, you can define arbitrarily as long as it's deterministic. So one very simple example is that you can sum all the characters and then you mark the table size. So what do I mean by sum all the characters? So you can map the character English character into numbers. So A equal to B, A equal to 1, B equal to 2, D equals to 4, so on and so forth. So that is 1 plus 2 plus 4. So ABD, it's the index could be 7, is 7 mod the table size, so 7 mod 5. Then once you do all this mapping, what will your table look like? And then of course that in practice, the hash function is much more complicated, but this just gives you an idea what exactly is a hash function and how does it link the value and the key, and then how to put it inside a table. Okay, now remember that we start with the search problem. Then how exactly do we use hash function to solve it? And then what would be the complexity? That would be a very simple exercise for you. And then the other will require you some mathematical understanding. Is that suppose I give you a hash function and then I tell you the data structure underlying the table is a size of n. Then how many items or how many values do you need to kind of insert into your table to guarantee that you can always find a collision? If you have no clue, the hint is the pigeonhole principle, meaning that what is the size of all your elements or your items so that you can find a collision, meaning the collision means that the values share the same key or same index in the table. Okay, so that's the take-home exercise. And hash function actually is still very active research area. And the big question is that we want to find a good hash function. So how do we define by good is that first we need to think about hash collision. Like as I mentioned before, I have two values B and B prime. If they share the same key, then that's a collision. Ideally, we want to minimize the probability of collision. And another thing to think about is that what happens if we have collision? How do we handle two values that have collision? And then what would be a reasonable table size? Because that usually hash function needs to deal with all range of inputs. So that ideally to save some space complexity, you want your table size to be as small as possible. Okay, so once you have this idea, then we can think about what's good hash function. First, of course, we want it to be very efficient, ideally like constant time in most cases, and then small collision, like not many values, they share the same key. And of course, we want to be deterministic, and then we want output, say HA equal to B. This B is always a fixed size output. And this is not always the case, but if it's a fixed size, later on when we see the application, we will find that this requirement, this property very useful. And how to define a hash function, how to do analysis is, I guess, very messy, so it's beyond the scope. But all we need to know just that there are many mature hash functions, including cryptography hash functions that we can use. And then the other thing that is some confusing terms is that hash map, hash table, hash functions, and I don't think there is a consensus on how we call them. So roughly in my video, I will use hash map as that the key is always an integer. So you can think of it as index of your table or index of your array. And then, but like for tables, actually, it could be arbitrary keys. It could be a string. It could be data structure. But like in real world, it's slightly different for different languages. So that when you want to use a particular language, check that what the meaning or the definition of a hash map or hash table. And another benefit of the hash function is that it's very useful to do data compression. So remember that the input size could be arbitrary. It could be very, very large. But like the output is usually fixed, and then it's the only proportion of your input. And then one classic application of this is the message digest. Suppose we have a very long message M, and then we just need to compare HM, just need to store HM in order to remember what we have seen or what kind of message we have received. Later on, we will see that this will be very useful, very practical optimization that people use all the time. Okay, so once we know hash function and in terms of Bitcoin blockchain, and then lots of security applications, we actually care about something more. We require more properties on the hash function. It's called cryptographic hash function. And some terminology is I give you a hash function and it's HA equal to B. And then in security world and actually in math kind of analysis, A is called pre-image and B is called image. And then you can think of A is an input to your function and B is just your output. So there are three properties that we usually care about for like cryptographic hash function. The first one is called one-way function, or we call pre-image resistance. So the idea is I give you Y, which is the output of some hash function, then it is very difficult or computationally hard to find the input. Okay, so that's one-way function. I hash it, and then you don't know what my input is. And then the different idea is that called collision resistance. It means that I don't have input. I just give you a hash function H, and then it should be very difficult to find any pair of strings x1, x2, or any pair of values such that hx1 equal to hx2. And then the final property is called second pre-image analysis. It's that I give you x1, again, it's some input. It should be very difficult to find x2 such that hx1 equal to hx2. Okay. So please take a minute to work out some example to make sure that you understand these properties, because later on when we talk about applications, these properties would be very useful, and then you need to understand it in order to follow the contents later. And then in terms of hard, what do we mean? There's a theoretical sense, because that when we talk about hash function, especially in theory analysis, actually there's a family of hash function that we are going to use. So when we say hard, is that the attacker that need to find some way to violate these properties, they need to consider an infinite family of hash function. And then we know that it's computationally impossible. But in practical sense, actually, that it's we still don't know how to do that. And then what we kind of care about is that there's no non-attack on on a certain hash functions that we can break any of the properties. So there are lots of practical functions you can use, your SHA-2, SHA-3, and then if you're interested in as a community, how do we come up with this kind of very complicated security functions? And then the NIST tell you how does the US figure out SHA-3, and then there's also other kind of hash function. And then one thing to remember is that In the old days, we have some very efficient hash functions, but right now people already know how to break it, and partially because we have more knowledge on math analysis, and then right now the hardware is so advanced, actually we can do lots of computation in a very short time. So like don't use SHA-1 MD5 for your any kind of secure thing. And finally, when we think about these three properties, one exercise to help you understand it is that suppose I tell you that I have a black box, it has an attack to break the second pre-image resistance. Then among the other, between the other two properties, which property will also be broken using this black box? Okay. So that's a take-home exercise for this part. And then next time we will talk about that. Once we have cryptography hash function, it's very, very useful. We use it for digital signature. We use it for MAC code as a message authentication. And in terms of Bitcoin or any kind of proof of work, hash pointer is the key for doing this kind of mining. Okay. So the takeaway is that we define hash function, we understand the hash function's properties, and I tell you that three applications, which we will look into more details later. All right, that's all. Thank you.